Hello Physical Science. We are going to start Chapter 16 today, and the title of Chapter 16 is Thermal Energy and Heat. Now, thermal energy was introduced in our last chapter. Thermal energy, if you remember, is the energy associated with all the microscopic particles that are in an object. They take the kinetic plus the potential energy of all the microscopic particles, and then now we're going to kind of transfer that to maybe a word you're a little more familiar with is heat. So we're going to look at how this energy of microscopic particles can relate to heat. So in our first section is going to be called thermal energy. So again, that energy of the microscopic particles, and matter. And one of the reasons why they're going to take a look at matter is because there was an accepted idea for a lot of the course of history that in order for a temperature to increase, there actually had to be some type of physical matter to cause that heat to increase. So if a temperature increased in something, they thought that there was actually some form of matter that had to cause that increase, and we actually know today that heat kind of travels in waves, kind of flows spontaneously. We're going to get to that more in depth throughout the course of this chapter, but to start this chapter, kind of to relate to that matter part, there's a guy by the name of Count Rumford, so that's a pretty cool name right there. His job was he kind of supervised the drilling of brass cannons in a factory in Bavaria. And from his observations, he concluded that heat was not a form of matter. So they talk about him more in depth in the book, about how, again, he's dipped it into water bath to show it cool down, and then it showed that the drilling process of making the cannons actually would increase the temperature of the water if you left it sitting in water, causing the water to boil, and kind of observed that, listen, there's no direct contact from any type of matter that's generating this heat. It had to be just kind of in the form of something else rather than something concrete and something solid that you can see. So we're going to talk more about his example first, but kind of a big overriding example from, or big overriding idea from his example is talking about how heat will flow, and what direction does it flow and things like that. So heat is the transfer, so to give an actual definition of heat, because that's going to be mentioned quite a bit, it's the transfer of thermal energy from one object to another because of a temperature difference. So I would definitely write that down, the transfer of thermal energy from one object to another because of a temperature difference. And then the next part is going to say how it does flow. It says heat flows spontaneously from hot objects to cold objects. So really, kind of when I had one of my chemistry or physics class, our teacher told us there's no such thing as cold, it's just an absence of heat, or just an absence of being hot. So cold is kind of a human thing that we generate, where scientifically there's really no such thing as cold. It could just be the absence of heat. So heat is going to flow from hot objects to cold objects. And again, this is kind of the example from Rumford. Again, he had a drill to make his cannons. So a drill was a machine that did work on the cannon. And remember that no machine was 100% efficient. We've learned that before, because some of the work done by the drill is useful, but some of the energy is lost to friction, and again, that friction generates a lot of times thermal energy and heat. And then he saw that heat would flow from the cannon to the surrounding water because the cannon is at a higher temperature than the water. And it kind of, excuse me, and that kind of just showed that, again, there was no concrete, there was no form of matter that was coming out of the drill to cause the water to heat up, or vice versa. There was no substance coming out of the water to cool down the cannon. It was just had to travel spontaneously in some way. It did not have any set form of matter in which it moved. So that kind of wraps up Rumford's experiment. Again, if you want to read more about him, we'll probably read more about him in class, because it gives kind of more in depth of what actually he did. And so now one word to kind of move on to, again, out of the history into more of like the current thing about what we understand is temperature. Temperature is a word that is always associated with heat. And temperature is related to the average kinetic energy of the particles in an object due to their random motions through space. So as we've gone on this year, this book kind of does a really nice job of building on itself. So we've talked about particles moving faster, and now we know, going back to our last chapter, the energy of motion is kinetic energy, so it's going to be, if it's going to have more motion, it's going to have more kinetic energy, and it's going to have a higher temperature. So temperature is the measure of how hot or cold an object is compared to a reference point. So we have to kind of have a point that we kind of monitor things from. And on the Celsius scale, the reference points are the freezing and boiling points of water. So 0 degrees is the freezing point, and then 100 degrees is going to be the boiling point. So those are our references to tell us how hot or cold something is compared to something else. And then on the Kelvin scale, there's a number that's known as absolute zero, and we're going to focus on this again a couple times throughout the course of this chapter. And it's defined as a temperature at 0 kelvins. So make sure you just kind of put that in the back of your head. I think we've talked about this term briefly before, but it's going to get brought up more and more as we go on through this chapter. And so as an object heats up, so again just focusing more on temperature here, its particles move faster on average. Again, we've talked about that before. And then the average kinetic energy of the particles is going to increase. So again, this is kind of just bringing a lot of the terms together, a lot of the ideas together that we've already learned throughout the course of the year. And that one way that heat flows is by the transfer of energy in collisions. So we've talked about that before. Gases in a closed container, when we increase the temperature, they're going to move faster, they're going to collide more. They collide more with the container. That causes pressure, which we've learned that before as well. And on average, if you're a high energy particle, you're going to lose energy during a collision, and then a low energy particle is going to gain energy during a collision. And overall, these collisions are going to transfer thermal energy from hot to cold objects. So thermal energy is almost always going to be, actually pretty much always is, hot to cold objects. Heat doesn't flow backwards. It's the thermal energy leaves the hot object and moves into the cold object, or to the object that has an absence of heat, if you will. And so, again, that's just to wrap up temperature now. To focus more on the thermal energy portion, there's two factors that are really going to affect thermal energy. And remember, I already gave us this definition, but here it is again, that thermal energy is the total potential and kinetic energy of all the microscopic particles in an object. And the two things that it depends on is the mass, temperature. Okay, so it has two variables, and right here it gives us three. So it depends on mass, the temperature, and the phase, whether it's a solid, liquid, or gas of an object. So those are the things that are going to affect thermal energy. The first way is how it depends on mass. So a cup of tea and a teapot full of tea can have the same temperature. So even though they have the same temperature, that doesn't necessarily mean that their thermal energy is going to be the same, because mass affects thermal energy as well. So the average kinetic energy of the particles is the same in both of them, so they're both of the particles are moving at the same speed. However, there is more thermal energy in the teapot because it contains more particles overall. So in order to really determine thermal energy, we cannot just look at the temperature, we have to look at mass as well. Mass is a big thing when we talk about thermal energy. Now because the teapot is bigger in size, it is going to have more thermal energy than the small teapot. And also, thermal energy is going to depend on temperature. So we have a cup of hot tea with a cup of cold tea. So in both cups now, our mass is the same. So mass isn't going to be our determining factor when we talk about thermal energy. Now we're going to have to take a look at temperature. So the average kinetic energy of the particles is going to be higher in the hot tea, so it's going to have a greater thermal energy. And then here another example to kind of talk about how it depends on mass and temperature. We have a cup of hot tea and a pitcher of cold lemonade, and even though the tea is going to be at a higher temperature, the lemonade is going to have more thermal energy because overall it has more particles. So that mass can override temperature, and kind of vice versa there. Since there's so much more mass and so many more particles in this cold pitcher of lemonade, then it's going to have more thermal energy than the tea. So I'll probably ask you on the quiz, what had more thermal energy, the small hot cup of tea or the large pitcher of lemonade? And you better know that the lemonade has more thermal energy because it has many more particles. And the last idea to go along with thermal energy that they're going to mention is something known as thermal expansion. And it's an increase in a volume of a material due to a temperature increase. So thermal expansion occurs when particles of matter move farther apart as temperature increases. So what that means is is kind of a cool example. If you take a balloon outside on a cold winter day, it shrinks in a process that's known as thermal contraction. Again, you've probably seen something similar to this before. The air in your tires gets low when it gets cold out. It's what's known as thermal contraction, because as the temperatures decrease, the particles that make up the air inside the balloon, they're going to move more slowly on average. And since they're moving more slowly, they're going to collide less often and exert less force or pressure, which we talked about earlier. And then the gas pressure will decrease and the balloon contracts. Now, it's not like the air is actually leaving the balloon. Again, if you let it sit for long enough, it might. But as soon as it happens, all that's happening is the particles are moving slower. And then if you bring that balloon back inside, it's going to expand again. And gases are kind of more subjected to this than liquids, and then liquids are usually expand more than solids. And again, that just has to do with the arrangement of the particles. Again, we've talked about this before, about how gases are more randomly arranged, and then liquids are a little more than that, and then solids are the most orderly arranged. And then one last example of thermal expansion is in a thermometer and an alcohol thermometer, because as the temperature increases, the thermometer or the alcohol in it expands, and then the height increases in proportion to the increase in temperature. And in an oven thermometer, strips of steel and brass expand at different rates. As the coil heats up, the coil will unwind, moving the needle on the temperature scale. So I know that was a lot of information. Again, a lot of interesting things kind of associated with thermal energy. A lot of things we might see in everyday life but not actually know what's going on. So that's it for the first part of this section. Let me know if you have any questions.